if we have a vector field F, and we have some curve, some closed curve in the plane, then we saw in the last section that the integral of F over a closed curve will be 0 if F, it'll always be 0 if the vector field F is conservative. So for instance, if this were a gravitational or electric field. But there's also many physically relevant examples where this will not be 0 and the vector field will not be conservative. So for instance, if this were, if this F is the velocity field of a fluid, then this integral will represent the circulation of the fluid. And a variant on this, if we change the integral a little bit, as I'll discuss, we could also use an integral to calculate the flow of the fluid in or out of this region. So we want a method to evaluate these types of integrals. So as motivation, if F is conservative, then we saw in general the integral from A to B of F, or sorry, so F is the gradient of some other function, so it's sort of like a derivative. Then the integral of F from A to B is F of B minus F of A. And it's useful to think of this as sort of like integral of F over a 2-point set A and B, where we specify sort of orientations. So if C is going from A to B like this, then we sort of give A a negative orientation and B a positive orientation. So we can relate the integral of a derivative along a curve to the integral of the original function on the boundary of the curve. So what we'll find, so Green's theorem, which is the subject of this unit, will tell us that we can evaluate this integral when F is no longer the big F is no longer the derivative of something. We can evaluate the integral of F over C by taking the derivative of F and integrating that over the region R, which is enclosed by C. So now this is the original, and C is the boundary of R. So here, this is in quotes. I'll have to specify exactly what kind of derivative this is. Okay, so let's talk about the concept of circulation density. So again, F equals mxy I plus n xyj is a vector field in the plane. So we're only considering 2D vector fields. And we'll imagine that it's the velocity field of a fluid. And the sort of math works out regardless of what f is, but this is sort of the most physically, we have the best motivation for it. So circulation density will sort of measure, like if we have, so let's say f is sort of like a stream flowing horizontally. So it doesn't seem like there's any sort of rotation going on just from this picture. But if we put a kind of paddle wheel into this stream, then we can see that this river will cause this wheel to rotate counterclockwise when viewed from the top. So in this case, yeah, here f is just I. Okay, so to see how to measure this, sort of measure this in general, let's consider a rectangle of width delta x and height delta y. So then this point is x comma y. This point is x plus delta x y. And this point is x y plus delta y, and then x plus delta x y plus delta y. And so the circulation, first say circulation is a measure. This will sort of have units, area over time. So we'll calculate the circulation by taking the horizontal component of f and then multiplying, so that'll be f dot I, and then multiplying that by the length of this. So we have we're multiplying, like f has units distance over time, and then we multiply that by another distance to get area over time. So the circulation along each segment of the boundary will be, so the bottom is f of xy dot I times delta x, and that will be m of xy delta x. Let me make some space. Okay, so that's sort of this direction. Then on the right, we'll take f of x plus delta x y, and we dot that with j to get the vertical component, and then multiply that by delta y. And so that now that is n of x plus delta x comma y times n of x plus delta x comma y times delta y. Now on the top, you can get rid of this picture. Since we want to measure counterclockwise circulation, along here we'll take f dot negative I, and we'll plug that in here. So the top is f of x y plus delta y dot negative I times delta x, and so that's negative m x y plus delta y delta x, and then the left, again, I'll say left is similarly f dot negative j, or f of so this is f of x y plus delta y dot negative j delta y, and that's m of x y plus delta y sorry, negative m x y plus delta y, delta y. Okay, so if we sum up all these contributions, so let's add left plus right. This will be negative, or sorry, yeah, left. Oh, I'm sorry, this was supposed to be n, not, yeah, sorry, this should have just been negative n xy delta y. Okay, so left plus right is n x plus delta x comma y minus n xy, and all of that times delta y. And that is approximately equal to del n by del x times delta x, and then that times delta y. And similarly, top plus bottom will give negative mx y plus delta y minus mxy, and then that times that times delta x, and again that is approximately negative del m by del y delta y delta x. So summing these, the total circulation around the boundary is approximately del n by del x minus del m by del y, and then we multiply that by, and then all of that times delta x delta y. Then, but if we divide out, so this is total circulation, so if we divide this out by delta x delta y, then this will be this sort of circulation per unit area. And so that's what we call the circulation density. Okay, so let me make this is a definition. So that's sort of where the motivation for this definition comes from. So the circulation density of a vector field F equals m xyi plus n xyj at a point xy is the expression del n by del x minus del m by del y. And note that this expression is a scalar, not a vector. This is also called so another term for this is the k component of curl. So recall curl F is nabla cross F, and so that's I jk del by del x, del by del y, del by del z, m, n, and then since we're in a plane, the z component of f is 0. So now when we evaluate this, we'll also del by del z of m and of n, so del m by del z equals del n by del z equals 0. So when we evaluate this determinant, we really just need to calculate this. So this will be del x, del n by del x minus del m by del y times k. So this will be del n by del x minus del m by del y all times k. So a notation for this we could write is nabla cross f dot k, and that's this. Or we'll also sometimes write curl f dot k. Curl f and nabla cross f mean the same thing. So how should we interpret this definition? So if the circulation density at a point x comma y is greater than 0, then a paddle wheel placed at that point will circulate, or maybe actually, will be pushed. So again, imagining this is sort of like a river or some kind of fluid, it'll rotate counterclockwise. Whereas if the circulation density is negative at a point, then it will rotate clockwise at the point. So, for instance, we already saw the example of f just being a constant. Well, actually, let me just say. So if we take, let's say f is moving at one point is like this, okay, but that doesn't tell us the general behavior, like it could be moving as we move around, it could be sort of turning outwards counterclockwise or outwards clockwise. So the circulation density is del n by del x minus del m by del y. So let's think about what each of these expressions is doing. So if del n by del x is greater than 0, that means as we move right, so in the direction of increasing x, the y component will be getting bigger. And so if we put all of these vectors to have the same tail, or to start at the same point, then we're getting a counterclockwise motion. Whereas if del m by del y is greater than 0, then that's saying as we move upwards, so in the direction of increasing y, the x component will increase. So if we again place all of these have the same tail, these will look like they're moving. This will be giving us a counterclock or a clockwise motion. And so this one's contributing to counterclockwise motion, this one's contributing to clockwise motion, and the circulation density will sort of be telling us which one of these wins out.